If you're just coming in, there's a bunch of papers up here handed back. Okay, the last time that we met, we were talking about, we were trying to finish up chapter 12, specifically 12.8, which was change of variables. And we had discussed this formula. I said that I didn't want to go through the proof of it because it required some things that we didn't have, that we don't have yet. And so we just need to be aware of this formula. Remember what it says is that if you have a double integral over some region D, that you can change the variables around and make your new integration region S and integrate now with respect to two different variables, but you always have to throw in this thing, the Jacobian determinant, when you do that. And we saw that when you did the polar, do you mind shutting that door while you're up, Josh? Good shot, too. When you do this for polar, right, you say x is equal to r cosine theta, you say y is equal to r sine theta, and then this piece right here becomes that r that pops out with polar conversion. So we're going to continue with this. We're going to spend a good probably 45 minutes to an hour on this, and then we'll move into chapter 13. All right, so visually, the idea that we have, you know, the one that I guess makes most sense to us is that if you're in the XY plane, if you have a region that looks like this, okay, and we call this region here D, then there might be some transformation, specifically the polar transformation, that takes you into a new region over here. Now I'm going to use, instead of r and theta, I'm going to use u and v. And what we know is that a circle in the xy plane with the polar conversion turns into what in the uv plane? So what are the restrictions on the two new variables? Like, let's act like they're r and theta, but remember that they're u and v. Right here, this region D, your radius is always between two constants, right? Yes? And your angle is always between two constants. So this circle in the xy plane would be turned into what in the uv plane? A rectangle, a true rectangle, the way we have thought about rectangles our whole lives. It would be a region like this, S, where our u variable, which might be the radius, is stuck between two constants, and our v variable, which might be like the angle, would be stuck between two constants. And it's much easier to integrate over this region than it is this, which is why we did polar conversions. So just keep in mind that our goal here for these first, well, we're only going to do 2 examples, all right, is to take a region that we don't want to integrate here and turn it into a region that we do want, that we prefer to integrate, or that may not be the problem. It might not be the region of integration that's causing us the issue. It might be the integral itself that's causing us the issue. So in the first example, we're going to have a region that we don't like. We're going to turn it into a region we do like. In the second example I do today, we're going to have a region that's okay, but the integral is terrible. So we do a conversion to make the integral better. Make sense? Yes? Okay. I will be referring back to this formula, all right, over and over. So just make sure you've got that with you, especially this Jacobian determinant where we have the partials. And let's get going. So I'm skipping example 1. I think I may have told you this last time, but I didn't like example 1, the way the book starts this section out. So just scrap example 1 in our notes. We're going to do this one right here. So we are going to be given a double integral over some region D. We're told that it's a parallelogram that has these vertices. And we want to make this change a variable. We want to change our x into 1/4 u plus v, our y into 1/4 v minus 3u. So look, I'm actually trying to point out to you that somebody is telling you what the conversion should be, right? What the change of variable is. You don't normally have that given to you. You actually have to come up with that yourself, which is going to be a bit of a challenge. All right, so let's just keep that in mind. We're being led into this problem on purpose just to get us to understand what's going to happen. So here's what it looks like, and I'm going to graph this by hand in a second. But this is what the actual region in the XY plane looks like. This is what the region in the UV plane looks like. So I'm just showing you right now that it looks like it takes this weird parallelogram that's kind of twisted, and we are turning it into, almost looks like a square, but it's rectangle. Well, it is a square. It's 8 by 8 square, which will be a nice region to integrate over. Now, could you integrate over this region? You could. It wouldn't quite be a type 1 or a type 2, would it? You would have to actually break it up. I'll draw on the board here. You'd have to go, let's see, maybe like, if that goes straight up, to the right of that line you could do a type 1 region, where you have a line on top of a different line. And then on this one you could do a type 1 again. So you could break it up into integrals and it would possibly work out. But that kind of defeats the purpose of the example, which is to show you how conversion, a change of variables can make your region a lot nicer. Okay, so there's two things we're really going to need to work on to get this integral. We're going to need to know what the conversion is, right? Why do we need to know what the conversion is? Well, you need to know what to change your x and y to, right? But for the Jacobian determinant, you need those partials, don't you? So you've got to have your conversions, which were given to us. And then the big piece is we need to know what this, we need to show that this parallelogram turns into this rectangle. And that's probably the most time-consuming part of the entire problem. So let's go after this. I have trying to do double integral over d 4x plus 8y with respect to area. And I'm given the conversion that u is going to be equal to, I'm going to write it this way, 1/4 u plus 1/4 v. I'm going to distribute that. So 1/4 v minus 3/4 u. Okay, so there's my conversion over. I will need, in order to do this problem, right, I will need my x as a function of u and v, and my y as a function of u and v. Do I have those? Can I determine x from u and v? Yes, right here. Can I determine y from u and v? Yes. So I've got these, and that's a good thing because I'm going to need to take the partial of x with respect to u, partial of x with respect to v, and so on and so forth when I do my Jacobian determinant. So that part I've got. The next thing I need is to know, I need to determine, I'll call it the image of D under this transformation. I need to know what happens when I take this parallelogram, transform the variables into u and v. What does that image of that D, that parallelogram, look like now? Now we know it should look like a square, right? But I've got to figure that out. I've got to determine that. So I will start off with a graph. Okay, I have my 4 points they gave me, right? So I'm going to draw a pretty decent graph on a new page. And I'll break out my graph paper to do that. I need my axes. This is my x-axis, this is my y-axis. I am going to take a little bit of time to pay attention to that because later on I'll have a graph and it'll be my u-axis and v-axis instead. So I'll plot the points. The points that were given to us were, what is it, 1, 5? Correct? So 1, 5. There we go. I'll label it 1, 5. And then I have negative 1, 3. I have 1, negative 3. And then I have 3, negative 1. And then I'll connect these with straight lines like this. So now what I'd like to do is I'd like to see what happens to this when I take it over to the UV plane through this transformation. So there's a couple of ways to look at this. I think I'm going to go the easiest way. I'm going to kind of trim down on today's lecture a little bit. But the transformation we're using, this is our transformation right here. I'll say this is like our capital T for our transformation. This transformation is a linear transformation, meaning when we look at x, it's determined by u and v, but both u and v are linear in the expression, right? It's not like u squared plus the square root of v, or even u squared plus v would be nonlinear now, right? Same with v. I mean, y. Y is a transformation in terms of u and v, but these are linear. If you have a linear transformation, this only works with linear transformations. Look, I'm going to bring up the note right here. Linear transformations take lines to lines. That's a huge deal. All linear transformations, if you have a line sitting here in some, xy plane, as long as the transformation is linear, then in the new variable plane, uv, it should also get turned into a line. And the points should also be taken to points. So what I'm going to do is I'm going to use that to try and determine that parallelogram gets taken into a square. Go with me? Using that idea. So what I'd like to do right now is I'd like to focus on the point 1, 5. I'd like to ask you, where does that go in the UV plane? All right, so remember, this 1, 5 is in the XY plane. I'd like to know when I transform it, where does it go in the UV plane? So all I need to look at is, well, what happens when X is 1 and Y is 5? Well, what's the information we know about U and V? Well, I know that what X was equal to 1/4 U plus 1/4 V, right? So I replace X with 1. Is 1/4 U plus 1/4 V. Everyone agree with that? And then the other thing I could use is the fact that Y is 5 would give me another equation that looks like this. 5 is equal to 1/4 V minus 3/4 U. Any questions on where I'm getting this information? All right, I'm going to not solve, but I'm going to kind of clean these up. I don't like the fractions. So I'm going to multiply both sides of this equation by 4 and this equation by 4. And I'm going to rearrange some stuff. So I'm going to get U plus V is what? For this first equation, U plus V is 4. And then this other equation, if I multiply everything by 4, I should get, how about negative 3U plus V equals what? 20, right? Isn't that what I get when I multiply and then move things around? This is now a system of 2 equations in 2 variables, right? You can solve systems of equations like this, linear equations, using substitution or elimination, right? I'm only turning it off because it's hard for me to see what's going on up here. If I were doing this, and so I would expect that everyone here could solve that system, all right? But if I were doing it, I would just do a quick switch over. To make my V's cancel, I'd multiply the top row by -1. So I'm using elimination technique. Leave the second row alone. And now once you have these V's will cancel if I add, I'm just going to go ahead and do that. So I add straight down. I get negative 4U equals 16. So U must be -4. Follow? Now, once I know what U is, I can go back into any of these equations, right, and find out what V is. So using, let's say, this first equation here, coming down here, I know that U is -4, so I get -4 plus V is 4, so V must be 8. So the point 1, 5 in the xy plane should get mapped over to the point -4, 8 in the UV plane. So I'm going to go back up here and fill this in, -4, 8. That makes sense? And now what I'm going to do is I'm going to do that for all the other points. And I'll set up a system of equations for each one. Now, would you like me to show you that, or do you think you could handle each of those systems? They're all the same, so your call. I don't care. Show you each of the points or not? No? 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 Okay, I can just tell you where they go? All right, so I'll put here, similarly, meaning using the same basic idea, we will know that, let's see, I just did 1, 5 went to, no, I didn't do 1, 5, I did, yeah, did I do 1, 5? Where is it? Hold on, I've lost my own work. Okay, there it is. Okay, 1, 5 went to -4, 8. And then 3, 1, 3, -1 will go to +4, 8. And then the next point we'll do is 1, -3 will go to, actually, I didn't do this one. I had done the first two, and then I figured you would do those on your own, or we would do those in class. But let's see. If we can figure out where this one goes, I think we'll be done. First one went to -4, 8. This one goes to 4, 8. So I'm going to guess this one's going to go to 4, 0. Let me see. I'm going to have to check it real quick, if y'all don't mind. Let's see. 1 must equal U plus V, 1/4 U plus 1/4 V. And then -3 must equal 1/4 V minus 3/4 U. Multiplying both sides by 4, U plus V equals 4. Multiplying both sides by 4 here, I get -12 equals V minus 3U. So I'm going to set up my two equations. -3U plus V equals -12, and then U plus V is 4. Does everyone understand that? I'm doing this one right over here. That's what this is. Replacing the X with 1, the Y with -3. Okay, so let's see. Switching that over, I'm going to change this sign to a plus, this sign to a minus, this sign to a plus, and now add straight down. We get 4U is equal to 16, so U is 4. And if U is 4, what's V? V is 0. Yeah, I thought it would be 4, 0. So that is correct. And then the last one, the last point, let's see, what am I missing? The point 3, -1 I haven't done? No. -1, 3 should get taken over to -4, 0. Okay? So let's see what that gets us here, all right? I'm gonna now go into another page and I'm going to draw the UV plane. And I think what I'll do is I'll put the XY plane next to it. I won't be as precise with my drawing here. It did something like this. I don't even remember what it did, but it was something like that, right? That was D. We had our 4 points. And now our UV plane I will label U, I will label V. And so the point here that we had 1, 5 got taken where? Negative 4, 8. So I'll count by 2. Negative 2, negative 4, and then positive 8. 2, 4, 6, 8. So that got taken here. I'll draw a little connector just to show you that got taken there, right? That's negative 4, 8. And then where did this point here go? Where did negative 1, 3 go? Y'all aren't going to help? 4, 0? I thought that was negative 4, 0, wasn't it? There was negative 4, 0? Okay, y'all are going to force me to go back. All right, I'll do that. Here we go. So look, the line that connects these two right here is going to be the same as the line that connects these two in the UV plane. So if I connect here, that line is where this line went. The linear transformation will take that line over to that line. Okay? And then we continue and connect. So where did the point 1, negative 3 go? 4, 0. Okay, so that went to 4, 4, 0 here. So the line connecting those two, I'll do it and highlight this right here, should be the same as the line connecting across like this. And then the last one, of course, I think we can kind of put it all together that this would be here. And so once we determine that this line came from here, there's only one other line left, right? It would be this one, which would connect those two. Okay? Nice linear transformation, takes lines to lines. In this case, took a parallelogram to a nice square. And this is now our region S. That's our new S region. And let's just describe S. S has two variables, right, U and V. It's the restriction on U and V. U is between negative 4 and positive 4. V is between 0 and 8. And so when I do an integral, double integral, my limits on my integral are going to be just constants, right? That'll be a good thing, as opposed to having to break this all up. Although you could argue you would have already broken it up and been done by now, right? Maybe? Okay. So we know what happens to D under this transformation. We just now need to figure out the Jacobian determinant. Then we're ready to do the integral. So the Jacobian determinant, I'll say JD, not Jack Daniels, is what the partial of x with respect to u, partial y with respect to v, minus partial x with respect to v times partial y with respect to u. And remember, x was 1/4 u plus 1/4 v. Y was equal to 1/4 v minus 3/4 u. So these partials are going to be pretty simple, aren't they? Just numbers. So the partial of x with respect to u is 1/4, right? Times the partial of y with respect to v, which is 1/4 again. Then minus partial of x with respect to v, 1/4, partial of y with respect to u, negative 3/4. And so we do order of operations, right? Multiplication here, so we get 1/16. And then minus the negative here would be plus not 4/16, 3/16, which adds up to be 4/16, which is 1/4. And then the absolute value of 1/4 is 1/4. So our Jacobian determinant spits out a constant. It's not like when we did the polar conversion, it spit out R, right? That's not a constant. R is not a constant, but it spit out a constant in this case. In fact, would you be willing to go out on a limb and say that if your transformation is linear, that your Jacobian determinant will always be a constant? Think about that. If this is linear, then when you take your partials with respect to u, if it's linear, then the derivative will always be the constant in front of u, won't it? The derivative here will always be the constant in front of v. And if this is linear here, this derivative with respect to v would be a constant, derivative with respect to u would be a constant. So in the case that your transformation is linear, you should always have a Jacobian determinant that's just a constant. Now, if your transformation is nonlinear, it's probably not going to be a constant. And it doesn't work out as nice as this because lines don't go to lines if it's a nonlinear transformation. So you might want to know how you would do that. And I think what I'll do is I'll show you how you do a nonlinear transformation, but I'll show you how we do it with this problem. All right? But let me just finish this out first. So our original double integral was over d of, what was it, 4x plus 8y dA. That has now been transformed into a double integral over s of 4 times x. What's 4 times x? It's 4 times 1/4 u plus 1/4 v, so that's just u plus v, isn't it? So I'm replacing x with what x is, u plus v, plus 8 times so 2u, what is it? 2u, no, 2v minus 6u. I'm just doing these two things, right? Here, here. Now, with respect to area, right, still, but it's the area of S instead of the area with respect to D. Like, but we know all this, oh wait, Jacobian, shoot, Jacobian, where's my Jacobian? Times 1/4, and then with respect to area. But because I know my limits of integration on my new variables, I can go, what, 0 to 8, negative 4 to 4, doesn't matter what order I go in. 0 to 8, negative 4 to 4. Clean this up a little bit. What, maybe 3v minus 5u. And then what? Pardon? Yes, that's what I was going to ask you, what you wanted to do with that 1/4 now. Just pull that out of both integrals, that's fine. But with respect to what here? du dv? And I'm going to stop right there. Because now it's just a normal double integral, antiderivative with respect to u, then antiderivative with, after you do that, plug in 4 and negative 4, subtract, then do antiderivative with respect to v, and you're in business. That's a pretty clean double integral now. Any questions? No? Okay, so if there aren't any other questions, then let me just show you how we would attack that problem had it been nonlinear, assuming that the lines didn't go to lines. And I think what I'll do is I'll just show you one part of the parallelogram and how I could figure out where that goes, and then the rest would be the same way. And if it doesn't make sense, you can tell me, and I'll do more if I need to. So let's take a look at, we had this 1, 5. And then we had 1, 2, 3, -1. So 3, -1, 1, 5. And if I connected these with the straight line, I could call this L1. Okay? And then the rest of the parallelogram, I have different lines, don't I? Now I want to know what happens to that through this transformation and acting like it's nonlinear. So I'm going to write down what my transformation is here. I know it is linear, but just try and follow this. Here's my transformation. I would like to know where L1 goes under the mapping of that. So what I'm going to do is I'm going to come up with a description of every point on L1. A way to describe all the points here. Well, it's a line, so you just need to come up with the equation of a line. The equation of a line represents all the points on that line. So this is a linear equation in the variable xy. It's a linear equation in the variable xy. So how can you find the equation of this line? There's several things, right? You could find the slope, right? And then use a point and use a point slope formula. Now, what I'm not doing is getting a vector equation of the line. Okay, I'm just going back to the old college algebra version of a line. So what is the slope of this line? Down 6 to the right 2, so -3. Can you tell what the y-intercept is? Well, if it goes over 2 units, goes down 6 and over 2, and I would need to get to the y-axis, I only need to go over 1, right? So I need to go, what, up 3 and over 1? So the y-intercept of this would be what? 0.8, right, up there. So I know that it hits up there. I'll squeeze some room in here. I know that this, following the same pattern, would hit at 5, 6, 7, 8. Should hit right there at 8. No, that's not 8. That's 8. So it should extend like that. So the equation of this line right here, L1, if I were to describe it to you, it would satisfy the equation y is equal to -3x plus 8. Agreed? However, there are some other restrictions we have here. My x-coordinate, because it's a line segment, my x-coordinate must be between where and where? My x-coordinates got to start here, what, at 1, and then stop where? At 3. Yes? So x is bounded between 1 and 3. If I don't bound x, then it draws the whole line, doesn't it? I just want the line segment from there to there. All right, so let's see how I'm going to use that information over here. All right? Let's see how I'm going to use it over here. I know what y is supposed to be in my transformation, don't I? Yes? And I also know what x is supposed to be in my transformation. So why not replace y here with all of this and replace x here with all of this? And then I have a new equation in terms of u and v, wouldn't I? A new equation in terms of u and v. So let me do that. Take this up here and let y be the 1/4 v minus 3/4 u. That must equal -3 times x, but x is 1/4 u plus 1/4 v, and then plus 8. Everyone see that's just a direct substitution of y and x into the equation that we came up for L1, that we came up with. Okay, so now at this point, I think things get pretty nice here. All right, things start to like cancel, I believe. distributing my -3 through. What goes away here? -3/4 u, right? That goes away, both sides of the equation. And then I get, what, bring this over here to the other side, and I would get 3/4 v added to both sides. That would give you v, which means the only thing left would be v is what? 8. V is 8. V is 8. Okay. So what would that look like over in my UV plane? Here's U, here's V, right? V is 8 is a constant function, isn't it? V equals 8 is constant. So I would go up, let's say 2, 4, 6, here's 8. I would just draw a line across, wouldn't I? Like that? That's what it would look like. Now, what if this had been something like V is 8u squared? Now, you'd have a parabola, wouldn't you? So it would have taken that line to a parabola. This just turns out, because of the way it was, a linear transformation, it turns out that our new curve is a line that's constant. It's kind of boring. But you would do the same technique if you wanted to do a nonlinear transformation. You look at this new equation, and you determine if you could graph it here. Does that make sense? And then you would do each of the other lines, and you would get, one of them would turn out to say that u is -4. The next one would turn out, oops, that's too far. This would be u is -4. Another one would be u is +4. And then this was v was 8. And if you do the last line, because right there would be 4 lines across our parallelogram, you do the last one, and it would turn out down here to be v is 0. And so you can see the region bounded by all of those would be in here. Whoa. What happens? Would be in there. Make sense? But I think knowing it's linear transformation and just taking the vertices and mapping them over is easier, right? Than doing it this way. But this is the way you do it if it were nonlinear. All right. Any other questions? Or, I mean, seems like I always ask for questions. No one ever asks questions. Any clarity? Make any sort of, no? Do what? Oh, yeah, sure. All right. So now, can I move on? Yes. Sometimes turns out that, like I said, you're not given the transformation. So like, look here, double integral over d of e to the xy over x minus y, where d is this trapezoid. So let's first look at the trapezoid and see, what we're faced with, see if we're even intimidated by this or not. All right? Get this out of here. See if this trapezoid is something you want to mess with. I still have my lecture notes out there, right? Okay. Make sure that you still have access to those. So we have this trapezoid. It has as its vertices the point 1, 0. I'm going to exaggerate this. I'm going to say this is 1, 0. And then 2, 0. So that would be here. This is our x-axis. This is our y-axis. And then it has 0, -1, which would be here, and 0, -2, which would be here. Those are the vertices of the trapezoid. So it looks like this. Do you have any issues integrating over that? Is it type 1 or type 2? You could split it as a type 1, couldn't you? You could do this right here, and then you could do this right here, couldn't you? Split it into 2. Do you have something due today, Josh? Oh, okay. I'm just wondering what you're working on. We could do this type 1, yes? But wouldn't type 2 be easier, like this? Well, no, you'd still have 2 regions here, right? You'd have to go this, and then you'd still have to split it. So no, I mean, but either one we could, right? Either way. So it's not too intimidating. The actual region's not too intimidating. But let's look at the integral. What if we were to try and integrate this e to the, what is it, x plus y over x minus y? dA? And I really don't care what our limits of integration are going to turn out to be. If I asked you to integrate that with respect to x, or with respect to y, either one, are you going to be able to handle that? Yeah? Maybe? You're trying to undo the quotient. We're trying to do the antiderivative, right? Yeah, that you see, like, look, let me just do one integral right here like this. I'll say dx. Try it with dx. Well, the problem is that the x appears both in the numerator and denominator, right? If it was just x upstairs, right, let's just say that x wasn't there, and let's say you just had y on the bottom, then that y on the bottom would be like a constant, right? And so you could kind of like forget that it's really even there. And then you'd be saying, what's the antiderivative of x plus y, or e to the x plus y? And again, the y is a constant. So that, do you agree that would be okay? Yes? You'd be comfortable with that? All right. But that's not what it is. And if I said to integrate with respect to y, then it would be really nice if that x wasn't in the bottom, right? Then you'd be able to handle it that way. In other words, what I'm getting at is that if the variable we are integrating with respect to was in the top or the bottom by itself, without the other variable there present also, then this might be an easier problem, wouldn't it? But I am kind of surrendering to it like as is. Should we see what Mathematica will do with it? Let's see if Mathematica can even handle it. I'm gonna see if Mathematica can give me the antiderivative, the general antiderivative of, make this bigger so you can see this, exponential, whoa, turn on my keyboard, exponential, that's like e to the what? I want x, was it plus y, divided by x minus y. And we'll go with respect to what? X, y, what do you want? X? Okay. Uh-oh. Uh-oh. What the heck is this? It's like an error function again. It gives us some sort of approximational result. So Mathematica is having trouble with this, and so would Wolfram Alpha. All right? So maybe there's something else we can do, and that's why we're here. So like I just said, this would be a little bit easier had it been something like this. Right? Let's say it was that. How about that? Wouldn't you like that? Or would you be able to handle that? Because really you could rewrite this as what? Y to the negative 1, just bring it up. Then the x is like a constant, and you're treating, I mean, that would be, that'd be real nice, wouldn't it? What would that be? If I brought this y to the negative 1 up, what would that antiderivative be? Could you do that? Would it be, how about with x, with respect to x? Would that be easier? Yes? Because then the y to negative 1 is like a constant? Okay. Okay, so let's, instead of investing time on trying to figure out these, because we're going to get our answer to something like this eventually. Main point is to understand the value of trying to get out of this double integral by making a change of variable. And so what change of variable could I propose? Well, let me just kind of throw something out there for you. How about if everywhere I see x plus y, I replace it with a u, and everywhere I see x minus y, I replace it with a v. Then that double integral would become e to the u over v, wouldn't it? And my new variables would be separated from each other, and I wouldn't have this problem of the x appearing on top and bottom like I do here. Seems like that would be too easy to do it like that, right? But it'll work. But here's the give and take to this is we'll be able to solve the integral, but now you have to be able to show me where that region goes, and you got to be able to compute the Jacobian determinant. As long as you can do that, you're free to do it. So let's see. Is this my transformation? Be careful here. What is it that I said that you needed to start these problems? You need basically two things. I need x of uv, other way around, x of uv. You need your x in terms of the two new variables you have. This is different than what I had last time, right? In the last problem, didn't I tell you x is equal to 1/4 u plus 1/4 v? Y is equal to 1/4 v minus 3/4 u? That's what I gave you what x and y were. Here, we actually had to say, I don't know, shit, let me just try and call that u and try and call that v. So I don't have my x in terms of u and v right now. I don't have my y in terms of u and v. I have my u in terms of x and y and my v in terms of x and y. So we're going to have to get to here first. And then after we figure out what that is, we're going to need to know basically what happens to d, right? Where does d go? And d is that region up here. So let's work on this part first, getting x as a function of u and v, and y as a function of u and v. We'll do that first, then we'll come figure out what happens to that region. All right, next page. I know that u is equal to x plus y. I know that v is equal to x minus y. So what do you think we can do here? Solve for y in both of them? Okay. Anyone have a problem with that? Good. So, I mean, there's nothing that says you can't do this. So if you solve each of those equations for y, you get that. And then set them equal to each other, right? You can set them equal to each other. Since they're both equal to y, then that tells you that u minus x must equal x minus v. Which tells you what? 2x must be u plus v. Which tells you that x must be 1/2 u plus 1/2 v. Right there. I have a nice definition of what x is in terms of u and v. Now what do I do to get y in terms of u and v? So I can go with, I mean, these two are already set, y is equal to this, right? So I could go in here and I could just replace that x, right, with this. Or I could replace that x with this. And then I'd have an equation that just has y and then u and v. So I'm just going to stick this right here into this equation. So what I would have was, can't fit that all on one page. Y equals, it was u minus x. So u minus x, but x is this, so minus 1/2 u minus 1/2 v. So y is half of u minus half of v. Questions? I have my u as a function of, or sorry, x is a function of u and v now. My y is a function of u and v. So I'll be able to take partials and I'll be able to get Jacobian determinant. Do y'all want to do that now? We can do it now. Is this a linear transformation? Yes, it is. It's linear, isn't it? And just look at it. X in terms of u and v are both to the first power. So I know that when I transform this thing, it's going to go from lines to lines, which I like. But that means the Jacobian should be a number, shouldn't it? So let's get our Jacobian determinant right here. So Jacobian determinant will be absolute value of partial of x with respect to u. Yes. 1/2 times partial of y with respect to v, so negative 1/2, then minus partial u with respect to, partial y with respect to u, which would be 1/2, then partial of okay, hold on. Partial x with respect to u, partial y with respect to v, minus partial x with respect to v, y with respect to u, which will be 1/2. So this gives me negative 1/4 minus 1/4, which is 1/2. There we go. All that for 1/2. So that's what our Jacobian determinant is. That'll get pulled out of our double integral. So now I just need to go see what happens to that region D. And I know that lines go to lines, which means points go to points. So if I can just figure out where the points go, I'll be able to just connect lines and I'll be done. Right? Seems pretty straightforward. So what are the points that we had? I have the point 1, 0. And then I have the point 2, 0. I have the point 0, negative 1, and 0, negative 2. These are all my xy coordinates. I want to know where they go when I map them over through this linear transformation to the UV plane. So can you tell me what u is if I give you what x and y are? Come back. I made a guess in the very beginning, didn't I? I said, look, I'm going to let u be x plus y. I'm going to let v be x minus y, didn't I? Then we spent some time getting that turned into x is something, y is something. But why not just go back to this? If u is x plus y, and this is x and this is y, then where does this point go? The u coordinate will be 1, won't it? And the v coordinate will be what? 1 minus nothing, so 1 again. That goes to 1, 1. Where does this point go? So to get the u, I let x be 2 and y be 0, so you get 2 here, and then what do you get for v? 2 again. So this is u and this is v. If I plug in here, what will my u be? What is it? Negative 1. And then what will my v be? Positive 1. And then finally, negative 2, positive 2. Is that all right? Just plugging x, y into those two equations and getting out your uv. We good? Okay, now I'm going to draw a quick picture here. It was like this. Right, 1, 0, 2, 0, 0, negative 1, 0, negative 2. That's my xy plane. In my UV plane, it becomes, let's see, the point 1, 0 went where? 1, 1 in the UV plane. So that went to the point 1, 1 right there. Where did the point, I'll label them the same highlight there. Where did the point 2, 0 go? 2, 2? So that's this point, which means that the line connecting these two should be equivalent to a line connecting those two. So that would be like this. Then where does the point, kind of like traveling around this thing, I'm going to go like this around it. From 2, 0, I'm going to go down to 0, negative 2. Where did 0, negative 2 go? Negative 2, 2, which would be negative 2, positive 2 would be up here. That's kind of weird. And so that point is that point. So I connect that pinkish one to the green one like this. And then my last point here, 0, negative 1, got mapped to where? Negative 1, 1, which is here. And I'm running out of colors. I still have this one. Okay, there we go. So I should have a point going from the green to the blue, light blue. So that should go like this. And then, of course, the blue to the yellow would be across. So our region here in the UV plane is basically the same thing as this one. I mean, it's not no better, right? It's still trapezoidal looking. But what's better? It's type 2. It's a type 2. But what's even better? The integral can be done. That's the key, is that your integral can be done. So now what I'll do is let's try and define this as a type 2 region. That means I'm going to be looking sideways like this. I need to come up with an equation for this line. And because I'm looking sideways, instead of looking at it like v is a function of u, I need u to be a function of v. So what is that line? It's just u is equal to v. It's the identity in uv. U is equal to v. No? What? Oh. Okay, yeah. And then now the other line comes this way, is the identity but negative. So that's just u is equal to negative v. And in our region here, S, that's our region S now, we have restrictions on the v, right? The v is between what? Two constants. And our u is between two functions of v. So this is not a rectangle in the UV plane. It's type 2. That's okay. Our v is between what two constants? Is that 1 and 2? We're talking about the height, right? This was 1. My line sucked here. Sorry. This was 1, and then this was 2 up here. So my v is between 1 and 2, and then my u variable is between where? Negative v and positive v, right? Now, that means the order of this double integral is going to matter, right? I can't switch the order because it's not a rectangle. So it's type 2. We have to follow the order of integration correctly. What else needs to be done here? I need to replace my integral, right? The x's and y's get swapped out, right, for u's and v's. So I think I'm ready to put the whole thing together now. We're going to have integral, double integral. The Jacobian determinant was 1/2. Here it is. I'm going to go from 1 to 2, and then I'm going to go from negative v to v. I'm integrating e to the u over v d u d v. That's it. So we made the change. I'm not going to carry it the rest of the way, but you see we made the change of variable. We have a new double integral. Everything looks pretty doable. You might want to practice that one on your own time, just to see if you can work that one out. Okay? It's always at absolute value. Because it's always going to be some other representation of the area, so it always has to be a positive. All right. That's it. That's it for chapter 12. I believe there's an assignment here at the end. Oh, so hey, look, if you were doing this problem on your own, now you know, like, I don't know, just try that being u and that being v. Just go for it, right? On your homework assignment, make sure that is the right page number. 721. No, how is that so off? Sorry? 12.8. Yeah, I'll fix the page number here. It's 749. Let me just make sure this is good. I don't know if I like those problems now. Let me see. Let me change this. Do 15. $17. And then 23. So I'll tell you the difference in these problems. On 15 and 17, well, 15 is just like the first one I did here today, where they give you the transformation. X is a function of u and v. Y is a function of u and v. It's a linear transformation. Everything works out great. 17 is a nonlinear transformation. I want to see what you do with it. But they give you what the transformation is. All right. Oh, wait, no, that's linear also. Okay, well, then you have another linear transformation. Great. The problem is you're not going from a line. Yeah, that's the deal. On 17, it's a linear transformation, but your region is not a line. So it's not taking a line to a line. It's taking something. It's like a parabola-looking thing, circular thing. So I want to see what you'll do on 17. And then 23, they don't give you the transformation. So you're supposed to come up with it on your own. So just see how you handle those. All right. Well, I said that'd take about an hour, 45 minutes to an hour. It took an hour, 10 minutes. Is everybody ready to start chapter 13? Excited? Calm down. Calm down, please. Come on. Look, this is it. This is the last chapter of the book. We're getting towards the end of the book. It's a good thing. All right, there's a lot of things to look at here, all right? So chapter 13 is the chapter on what's called vector calculus. So we're going to do a lot of calculus, but now we're going to throw the vectors into it. When we were talking about vectors before, we never even really did, we did some derivatives of vectors, but we really never did anything other than the derivatives of the vectors. So now let's see how we can bring vectors into integrals and see what happens, okay? So first we need some understanding of what a vector field is. And you can make a vector field a very complicated concept or a pretty simple concept. For us, let's keep it simple, very visual. Okay, first of all, a vector field in two-dimensional space says let D be a set in the plane. A vector field on the set in the plane D is a vector function. So a vector field is a vector function. It assigns to each point x, y in the domain a vector. And here's the visual. All right, so here is two-dimensional space, right? Every single point in this two-dimensional space is an ordered pair, right? Not a vector. Every point is an ordered pair, has an x-coordinate and a y-coordinate. A vector field defined on this space assigns to each point in the actual space a vector. Now, a vector is a directed line segment, right? It's a segment of a line that has a direction and has a magnitude. So I can come in here and I can make up any function I want that tells you what the vector is that you should assign at each one of these, at each point here. The vector field we're looking at right now is the vector field. It says, look, if you're at the point x, y, I want you to create the vector negative yx at that point. So if I'm at 0, 0, I'm going to plug in 0 for y or 0 for x and y up there, and what vector does it spit out? The 0 vector, which is right there. Isn't that the 0 vector? All right. Now let me move. If I move over here to the x, the point, the ordered pair here is the point 2, 0, right? If you plug in 2 for x and 0 for y, you get the vector 0, 2, which starts here, goes up 2, right? Yes? Now let me move up a little bit. Let's go right there. So now I'm at the point 2, 2, right? So I'm plugging in 2 for x, so that stays the same. I'm plugging in 2 for y, so now I get an x component of negative 2. So that means I go to the left 2, up 2. That's my vector. And everywhere I move in here, there is a vector, right? Everywhere. So it's impossible for me to show you all the vectors, right? I can't show you all of them because if I show you all of them, it'll just look like a big black, right? It'll just be black. The whole sheet would be black. So what I can do is pick some arbitrary points and ask the computer to show me what the vector looks like at each of those points. And now these lengths are not true lengths, but you can see what's happening. According to this diagram, it looks like as you move to the right, the vectors are always pointing like upward, but it seems like they're getting longer as you move out to the right. And let me see if my point actually matches that. Bring this one back up. Okay, look at that. See, all those vectors over here are pointed up, and then as I move to the right, the vector is getting longer. So you see, that's why these are getting longer than the ones inside. Yes? And there seems to almost be this like twisting motion happening. So this is where we start to use the idea of like magnetic fields, things like that. You know, you're standing there, there's wind blowing, things like that. At every point, if I'm standing at the origin, right? If I'm standing here and this is wind, then there's really nothing acting on me, right? I'm just kind of, and everything around me is chaos. I come out here, it's stronger and stronger wind, and if I were to let go, I get swept up in it, right? So that's your vector field. Now, we could ask the computer to put even more vectors in there for us if we wanted to. All right? Questions? So a vector field is a function that assigns to each ordered pair in the two-dimensional space a vector. Now here's just a general vector field. So I made this one where you can tell me what you want me to put in here for your vector field. So that's what negative yx looks like. You want to try something else? Go ahead. What do you want the vector function to do at the ordered pair? 2y here, and then what do you want for the other one? Negative x squared? Sure. Okay. That's what that one looks like. So you got a lot of different things happening here, right? As you're moving through this. Very strong, long vectors pointing downward here, right? As you move to the right, these kind of start to twist and then they start to come back. So, I mean, you can kind of get a feel when you when you have the computer give you a bunch of them, right? What's happening? The only way to do that, to get a feel for it on your own, is to actually go and test a bunch of points. So it's somewhat difficult to just look at a vector function sometimes and tell what's happening. How about this? How about a vector function that does not take the y coordinate into account at all, just does the x coordinate? And I'm going to make it sine x. So the x component of the vector field is sine x. The y component of the vector field is negative x squared. And let's just see what happens. So y shouldn't matter, right? Y shouldn't matter. So do you see that no matter where I am, the y coordinate, the vector is going to stay the same? Watch, if I move this up and down, right, that vector doesn't change. Now if I move it left and right, it's getting smaller, then larger. And then I'm not zoomed out enough, but do you think it's going to point the other direction? Let's see, your y coordinate, your y component is always negative, isn't it? So you're always pointed downward. The x component is changing, isn't it? So the x component of this vector right now, the x component to the left, there's some left to this vector, right? But what happens is I keep moving to the right, it's going to go, and now the x component is what? 0. And if I go past over here, what should the x component be? I wish I could, you know what I'll do? I'll change the period of the sine function so you can see what I'm trying to get you to see. There. You know what? I'll make it 4 pi instead. Okay, so watch the x component of this. All right. X component is what here? It's pointed to the left. So it's negative, right? X component is, shoot, that went too fast. 0, now it's positive, now it's 0, then it's negative, now it's 0, now it's, see, what I'm talking about is the left and right of this vector is going back and forth between what? Being negative and positive and negative and positive, because the sign is controlling it, right? And then the y component just keeps on getting bigger. Okay, I'm just having fun with this now. But there's nothing that says you have to have a vector field in 2-dimensional space. You can also have a 3-dimensional vector field where at every point, every ordered triple in 3-dimensional space, you assign a 3-dimensional vector to that point, f of x, y, z. The vector field, or the vector function, f of x, y, z. Now, vector fields in 3-dimensional space are harder to visualize, even with the computer. I mean, I can have the computer compute the vector at each point in 3-dimensional space. I don't have a problem having the computer do that. Where I start to have issues is where I try and get an idea of what's happening everywhere. And so I can have the computer do this. Usually it slows the computer down here. Let's see what happens. Here comes, the computer's going to put a bunch of points in and show me the vectors. And yeah, now let me try and move it. Yeah. Not really easy to see what's going on there, right? Oh, yeah, now the computer's like really not happy with me. Maybe I should go to a course, see if I can get this back. Okay, that's a little better. I think the computer will be able to handle the rotation here. So I'm spinning this around. It's still really difficult to see what's going on, right? But the idea is there. At every point, you have a vector. So this is good for, like, think about now in three-dimensional space, gravitational forces, electromagnetic fields. Again, the same thing, magnetic fields. Look at this vector field. Here's the definition. Negative x over this, negative y over this, negative z over this. And I'm going to move it around, and I want you to take a look at the vector. Tell me if you notice anything. It always looks like it's pointed towards the origin, right? In fact, if I bring in the actual vector field, everything wants to go to the origin, right? This is a great example of a vector field that we can use to describe gravitational force. Because the force is always center-seeking, right? It's always center-seeking, always going to some point. Now, what we also understand, though, about gravity is that the force is actually dependent on your distance, too. The closer you are, the further you are. So you would have to maybe tweak this to get it to work, to represent what's happening on Earth or what's happening on different planets, right? Make sense? But it's a center-seeking vector field, which is really cool. All right, now, remember that when we first started talking about functions of two variables, we called this function a scalar function. And when we graphed them, they were surfaces, right? A scalar function of two variables is a surface. And we also defined back then the gradient. So I remember coming out here and saying, imagine we have a surface floating out here, and I walk out and I go to a certain point on the surface and I say, which direction do I point in to have the maximum rate of change? And we said that's always going to be in the direction of the gradient. So we said, well, what's the gradient? The gradient is the partials, right? So if anyone gives you a scalar function of two variables, you should be able to compute the gradient. And the gradient was a vector. Do you remember this notation? And since the gradient is a vector, both in the two-dimensional and three-dimensional cases, since it's a new vector, and that vector depends on the coordinates of the point, x and y, or in the 3D case, x, y, and z, then wouldn't you agree that the gradient actually defines a function? A vector function? And so we call it the gradient vector field. So the difference is this. If I give you a vector field, here it is, right? If I give you a scalar function, it gives you a surface. But we know that we can always define the gradient of this scalar function by computing the partials. And that is now our new capital F, and we can call that our gradient vector field. We'll see the value of it in a little while, but just the main point is you can always generate the gradient vector field from a scalar function by finding its gradient. So given this vector field, let's please compute the gradient vector field. So what is it? Do we need to go through it? Should we go through it? What's the gradient vector field here? Let me try and do this way here. I know it's been so long since we've... Okay, the gradient of f is the partial of f with respect to x, partial of f with respect to y, written as a vector, right? So what is the partial of f with respect to x? 2xy. What is the partial of f with respect to y? 3y squared. Y'all remember doing gradients? This right here, if I wanted to, I could come in now and say, hey, I'm going to define a vector field as 2xy x squared minus 3y squared. I'm going to choose to call a vector field that. Now, by itself, it's just a vector field, right? But the fact that it came from the gradient of a scalar function makes it a very special kind of vector field. We call it a gradient vector field because it's the gradient of something, right? It's the gradient of some scalar function. Nothing new here other than some terminology. But this is the big kicker of it, all right? This is what we're trying to get to because this is going to help us later, all right? Conservative vector fields. A vector field F is called a conservative vector field if there is some scalar function f such that f is capital F is the gradient of little f. This just means that the vector function is the gradient vector field of some function f. So look over here. Is this right here a conservative vector field? Is that a conservative vector field? Yes? Why? That's right. It satisfies. It is the gradient of a scalar function, right? That's where we got it from. Right? That's where we got it from. So if someone gives you a scalar function and says, hey, find the gradient, you know that that gradient vector field is always conservative. Right? The big thing for us will be, if I give you a vector field and I don't show you where it came from, can you tell me if it's conservative? Without showing, so imagine I didn't give you this example. I just gave you this. Can you come up with the little f this came from? If you can, then you can tell me it's conservative. If you can't, you can tell me, I think it's conservative. Right? That's about all you'll be able to do. So it'll be one of our tasks later to figure out if it's a conservative vector field or not. And then see, what we'll see later is that if it is a conservative vector field, then there are some very nice results from that. But we have to first be able to say it's conservative. What do we have here? Of course, that's the wrong page. I'm slowly getting this updated, though. There's really not a whole lot in this 13.1 section, because a lot of what they want you to do is draw vector fields by hand, which is just, to me, it's a good exercise, I guess. Let's see, so number 1, sketch the vector field. Number 4, sketch the vector field. You know, maybe try a couple of points, just practice with it. 21 through 24, find the gradient vector field. Those you need to do. Just practice taking your gradients again. You want to see the graph of that one? I think I have it right here, actually. Yeah, that's it right there. Bring them in. Can you see it? It's what we're doing is, and I didn't make this connection yet. We can make it next class also. But look, this is a surface, right? This is a surface. A scalar function, little f. We took its gradient and came up with a vector field, right? This is what that vector field looks like in two-dimensional space. So imagine now that you're looking at the surface from the top. Looking at it from the top. Right? This is the view from the top, and you can see the vector field transposed on it, right? And I have these weird, like, contour lines. These contour lines represent, like, a steepness. The long vectors represent large gradients. And so it's like if you put a ball somewhere on this surface over here, if you put it on there and say down was into the paper, then gravity would start pulling it. Then it would start rolling, right, and start going in different, some direction. Well, the gradient vector field shows you like where you'd be headed. That's what it's going to show you. Now, it's opposite because the gradient was always pointed in the upward direction. So you'd want, like, if you were to put a ball right here, you would actually roll this way. If you put a ball here, you'd roll this way. You'd roll really fast this way. It's same thing like on the news when they talk about weather. They talk about, what are those called? Those lines. No, not isobar lines. I forget. They say that the more packed together they are, the windier it's going to be. And then they space them out, and it's going to be that windy that day. I don't know. If you ever watched the news, the weather guy standing there, or weather lady standing there, no? Just look at it. They show the wind. I think they're called isobars. I could be wrong. But it's basically this. The more packed together they are, the higher rate of change there is. The more spread out they are, the lower rate of change. Which you can see, these are tiny little vectors in here. The bars are not, they're spread out. And then as we get closer this way, they're compacted in. It's like a contour map for elevations, in another way. The more lines there are close together, the steeper the elevation. The more further apart they are, the less. Kind of makes sense? Is that what you wanted to see? And then let me see if I could find this. So I think what we're looking at right here, see this front edge right here? This right here? That edge, I believe, is this right here. So if I were to put a ball right up on the top of that, it would roll. It would want to go down that ledge right there. That would be here and then going that way. And then on this way, this side right here would be this back side. You can see it dips down. So that would be, if I put a ball here, it would want to roll that way. Remember, it's going to want to roll against the arrows because the gradient's upward direction. So it goes like that. That's right. Yeah. Think about it this way. This is actually, I hadn't thought about it this way, but imagine that you have a plane. Let's say you just have your surface is the XY plane, which is the ground, right? What's the equation of that plane? F equals 0, right? F of x, y equals 0. Or let's say the plane is the ceiling up there. Let's say z equals 10, or f of x, y equals 10, yes? What's the gradient of that function? What's the gradient of the scalar function f of x, y equals 10? What's the gradient of this? What's the partial of that with respect to x? 0. What's the partial of that with respect to y? 0. So you get the 0 vector, don't you? That's the gradient. That means that if you put a ball on top of that surface, right, where's it going to want to go? Nowhere. It's happy, just right there. It's flat. It's just going to sit there. There's nothing pulling it in either direction. Kind of make sense? Okay. All right. Well, we'll pick up. We've got a lot more to do, but at least we're close to being on track. 13.2, we were supposed to, I think, finish today, but yeah, no, we're not. That's not going to happen. 13.2 is long. Got a lot to do in 13.2, but we're ready for it now. Y'all have a good rest of your day, right? I know you want that take-home quiz. I'm working on it. I almost have it ready. I'll probably email it today. Hey, Josh, I was asking you because I saw you in the tutoring lab or little thing, and I saw you working real hard on something, so I thought you had something to do today or something. All right. Everyone left. Who left back in that corner? know who it was. Hold on, I need to see his name. See who's here. He's the only one. Josh, I got you already. Allie, you're good. I know you always have to wait till the end. Dan Patrick was here. Josh Shaw was here. Excuse me. Thank you. Thomas was here. Raul, didn't show up? Jose Riojas? Tamara, you're here. Josh Shaw's here. Jose Aguilar, that's who it was. Gregorio's not here. Diego, got you. I got your email. Yeah, that was the worst possible thing in the world. Get in my car while it's pouring down rain. So the turn it on, I just hear it fly off. Took like an hour, almost an hour and a half, just trying to put it on. Couldn't see what I was doing. What did you lose on? My serpentine belt. Yeah. Usually takes like 15 minutes, but with all that rain that was coming down, well, I had the last serpentine belt that I did was about 2 months ago. My cousin, I forget what kind of car it was, Nissan. Yeah. And front wheel drive, engine sideways, and the space to get on the bolt. Like this much on the sensor. Yeah. So I had to get a special tool from the auto place that is designed just for getting that bolt off. I had to. I've done it before. It's a nightmare. I actually need to replace the belt. It's crazy. Yeah. But yeah, mine's the same way. I drive a little 4-cylinder DX3 hatchback, and my engine sits sideways. And in order to get into there, there's like this much clearance, but on top of that, my sensor's on the back end. So then I hit the axle. If I don't have a tool long enough to get up in there and pull all the way down, I was like, "Yeah, kidding me?" The rain all in my face. I was dirty as hell. I just got out of the shower. I was just like, "Oh, I'm gonna have to take class today." Well, thanks for letting me know, but yeah. So, have a good day, bro. You too. Sir. Think so? Have you looked at everything? What? You got. Okay. Okay. All right. So, do you want me to do it, or do you want to do it yourself? If you send me an email, I'll do it. Yeah, just because as long as it's official, like that I have documented through Canvas that you requested, then I'll do it. I like to. Oh yeah. Anytime. Yeah. Do you want to wait until the last day to? Is it Friday or Monday? I thought it was Monday. I thought it was the 17th, but maybe it's. Yeah. Well. Well, whatever you think is best. Just don't send it to me the last day. Give me at least, because the way it works is if you send a request, even if I don't do it, it'll still be okay because you'll have it documented that you requested before the day of. Okay. I'll send it to you today tomorrow. Okay. Okay. Yeah, and feel free. You can come in anytime, even if you decide you have to do that. Thank you. All right. Yes? The what? This right here. Yeah, what you have in this picture, you have this thing, right? And you have it on top of this triangle thing, which looks like that on the ground. you're looking at that volume right there. That's what that integral is. Okay? But you're looking for the volume between above the tetrahedron. So what you needed was, there was a tetrahedron that went up like this. I don't remember how it looked, but, right? So this right here is the bottom of the solid. So you should, that's right. So you should have, and maybe I missed it in here, but you should have had the 16 minus x squared minus y squared. That's the top surface, right? That's this. Minus, now the bottom would have been that surface of the tetrahedron, the face of the tetrahedron. So you would have had to have got the equation of this plane. Did you do that, or? I know you got the thing on the ground. You got that? But did you get, like, yeah, this, yeah, you need that. Was that the ground, like the bottom part? Yes, yes. Let me try and exaggerate it. Let's say you had the solid, again, this thing comes all the way down, right? All the way down the ground, flat down here, right? And there's your triangle on the ground, whatever. But you need that surface, that tetrahedron. I'm going to say it goes up like this. It's really exaggerated. Let's just say it does that. Then it actually cuts out all this volume from it, right? And so now this is what you have remaining, this piece here. So that's different. So you're missing that part of it. And how do you get the equation of this plane? You have to get, yes, just that part. So the question is, what is that as in terms of z? Because you have to get it like a function of x and y. So the reason why I took off a lot for that was because to do it, you had to remember, okay, I have 3 points. I create vectors. I cross the vectors to get the normal vector of the plane. And then you have a point and a normal vector. Remember that? And that's how you get the equation. Okay. Yes? Yeah. Okay. Everything else was perfect. I believe these were with 25 points. I believe there were 25 points apiece. So you didn't, I mean, you got a big chunk of the problem was done, but there's a big chunk missing too. So, okay? All right. All right, no problem. Yes. I believe that the maximum we could have gotten on it would have been higher. Would you send me an email and say, can you compare my grade with, replacing my whatever quiz it is with the bonus? Then I'll look at them both. And once I run, I'll just have the computer tell me what the difference is, and whatever's better for you, I'll go with that. Okay? Doesn't have to be long and drawn out. Just tell me what quiz you want me to look at, and remind me that you got 8 out of 9 on that midterm bonus thing. All right? Or the next time you come by my office, we can do it. Whatever works best for you. And then you said you were going to drop a quiz. You will get one dropped quiz. And then what about the in-class quizzes? Do they all stay the same? I think those will probably just stay the same. Yeah. You have a good day. outside than it was earlier or something? It's colder in this building. I don't know. It's cold indoors right now. It's warm, right? Okay. I don't know why it's getting colder in this building. I guess they had to turn the air conditioner on. Related rates quiz. These don't have the grades on it, but the grades were put up online. Aaron, Tyler, Ernest, Sarah, Paul, Kevin Baldunas, Jorge, Honor, Rodrigo, Kyle Keller, Ruben, you might have something there. Is that what it is? Is it time for what? Oh, we'll see. I'll find out. No? Oh, Mark, right? What's your last name? Oh. What? Mark. Oh, yeah. You might have something here. The grade is online. I didn't put them on the assignments. What's that? I just graded this one. I think I saw that one. Well, which one am I supposed to grade? No, that's because I had asked you. I was like, do I just give you both? Yeah, just put both. Yeah, but what do you mean both? Because you had two different ways of doing it? Yeah. Oh, maybe I misunderstood you. Okay. No, it's okay. Let me see what the correct answer was. I was like confused. I was like, man, there's two ways I can like do this, and both gave different answers. I was just like, Well, why is this one different though? What's wrong? Because on this time,
what I did on this one is that I plugged it in for being at 1 second time, everything, and on this one I just plugged it in for being at yeah, 'cause I multiply. You know how there was like the you multiply. I multiply as if it was 1, so 370 times 370.
Yeah, that's the right way to do it.
That was the right way. Oh, okay.
Yeah, because you had to 3 seconds after they are fired. So you have to know 3 seconds after they're fired. This one's a 750, right?
Yeah, 250.
Yeah, but it's times.
Oh yeah, 250 times. Well, it's 250 times 250. It's a huge number. I just divided it by. So.
Yeah, see that should be 750 there.
750 times 250.
Because if it's been that's the distance it's traveled after 3 seconds. If you did times 1, it should be 250, but it's 3 seconds later. I know, but the fact that worked out was just purely.
Well, because I did have it there, and then I just showed it a different way. Because that's one here. Yeah, I showed it on the 3. Because I see what you're saying. You had the 3 seconds on the outside of them, and then you had the 1 second on the inside. For me, I did it like there's so many eraser marks. I had done it like that, and then I was like, that's why I turned them both. I was like, you know what? I know that doesn't seem right, and
Okay.
that's why I was like, well, maybe I had to plug in with it at a second, and
Yeah.
that's why I asked if I could turn them both.
Okay, I guess I misunderstood when you said that. I didn't realize.
Yeah, sorry, I should have made
okay.
it.
I just when I first graded it, I thought, okay, the one with the question mark, he's not sure about. This one looks more like it was written to be turned.
Yeah, because that was my very first written out one. I was like, that can't be right. So I read it. So.
Okay. Well, you know what? Keep it for now,
okay.
and I'll make a note of it.
All right. Yeah. No problem. Thank you.
All right. 4 point what? We will get to the mean value theorem today. We are going to spend a little more time on max mins because we've just scratched the surface on that. I think for homework I've given you. Let's see here. 23 through. So we hadn't really gotten into some of the tougher problems, which is what we'll get into today. There's the related rates assignments are up here if you want to pick up. We will get into 4.2, but we're going to spend quite a bit of time 4.1 still. Did you do 4.2? Yeah. Feedback theorem. There's not a whole lot on that section. Right? So it was pretty. Yeah, it's pretty short. So. All right, well, let's get going. Holy crap, I've been recording this entire time. From my last class.